Symmetric functions are a technical tool that was mentioned yesterday. It shows up in a lot of these problems in statistical mechanics. And the goal of today's lecture, so it probably will appear dense. I'm not really going to do any proofs. I'm going to tell you what there is, the most important things about symmetric functions and how they appear in various settings. And there are going to be a lot of formulas. I'm going to put the slides up, so don't worry about taking notes or anything like that. The point is that you can actually, later on, when you see this some formulas, you maybe will make a connection. This looks like a Schur function, maybe, or a determinant and things like that. And so to warm up, let's start with, okay, before we get to the technicalities, just a brief overview of where this is really going. So what are we using these symmetric functions for in our context? One is to analyze lozenge tilings that you saw this morning and yesterday in many, many pictures. So they can be used in various different ways to study pictures like this. The other is asymptotic algebraic combinatorics and representation theory, which may not be immediately apparent why it's connected to this workshop, but hopefully I'll tell you tomorrow why pictures like this is a limit shape different from the ones that Igor was showing yesterday. This is the Vershik-Kerov limit shape here. How this shows up and what it has to do with some statistical mechanics models. So we'll do applications and generalizations tomorrow. Today it's going to be the basics. So let's start with very basic combinatorial question. If I want to choose k numbers, non-negative integers, such that they sum up to n, it's called composition. I'm not, we treat them as a vector, so permutations of the entries make different compositions. So how many of those are there? It's a question. You remember the formula?
Negative binomial coefficient.
It's a binomial coefficient.
Negative binomial, even.
Yeah, it's a negative binomial coefficient, but we can write it as a positive binomial coefficient like that. Okay, that's relatively easy. Undergrad level combinatorics. Of course, my students always get confused. So what do they get confused with? The next thing, integer partitions that Igor was telling us about yesterday. So those are, it's almost like this, except now this time we are ordering the integers in weakly decreasing order. So we are not going to do permutations. So if we have 3 integers that sum up to 5, we just have 2 partitions as opposed to 6 that were over here. So this is a different combinatorial object. So how many?
You allow 0 in the first row, so A1, AK, and then Z non-negative?
Yeah, Z non-negative. So we can do that in positive, then it's going to be a different binomial coefficient. And -1 choose K -1. Yeah. But let's say for the integer partitions, we restrict ourselves. So how many are there? That's okay. There is no, this time there is no good answer. So there is no formula. It's the number of integer partitions regardless of the length and the number of non-zero parts. So that's how we denote a partition of n. It's going to show up all the time, lambda. This is v dash n. This means a partition of n. It's going to appear everywhere. So the Hardy-Ramanujan formula is telling us that asymptotically it's something like this. This is not easy to prove. And certainly not obvious. But what can, so if we don't have exact formula, what else can we do? Well, we can have a generating function, right? So that's also what Igor was showing yesterday and goes, in this case, let's say from 0 to infinity. The number of partitions of n, q to the n, is this beautiful product. So this is due to Euler. Okay, so what else are we gonna do? So we're not gonna spend much time on integer partitions. We're gonna move further. So let's visualize first these partitions. We visualize them as a Young diagram. So the number of boxes on each row is given by the number of the integer that's called the corresponding part size. So of our partition 5, 3, 2, it's a partition of 10. It can be pictured as this collection of boxes justified on the left. And how many boxes we have? Well, whatever it is partition of, so in this case 10. So this is called the Young diagram. So the same generating function I wrote earlier, we can write it like this. If we sum over all lambdas, these partitions, q to the size of lambda is the same thing as before. And now we can play the first generalization. We can put numbers in those boxes so they're weakly decreasing along rows and down columns. This is what's called a plane partition. So each of these rows itself is a partition, so it's a weakly decreasing collection of integers. So, but now we have a grid. So they'll form this shape. Let's say we don't really restrict the shape in this case. We just sum over all possible arrangements of non-negative integers. And when we have zeros, then it's going to be zeros all the way, so we can ignore that. And let's say the absolute value in our context means just the sum of the individual parts. So what's the formula for those with whatever restrictions you want? No chance of writing down a formula, but we can write a generating function. Kind of suspicious. It looks like what an undergrad would make as a mistake. So you take this, each of this 1 minus q to the I to the I. I mean, how can this be correct? Right. So we'll use this as a motivation. We'll try to prove this in several different ways here so that we can put these symmetric functions I'll tell you about in a moment in context. Okay, so quickly, why should you care about this here in this audience? What's a plane partition really in this, guys? So let me put this in 3 dimensions. We're gonna put this flat on the plane. We have these numbers written down, and on top of every number, I'm gonna stack as many boxes as there is the number written over here. Boom, what is this? We can put some walls. You saw it this morning. Okay, this is a dimer cover of the hexagonal grid bounded by the hexagon. So, or a lozenge tiling of the hexagon. One of the most classical objects that shows up in statistical mechanics. So this plane partition. So what I showed you earlier was some kind of a q to the volume statistic generating function for this plane partitions. Okay, so the goal is to figure out how to understand something about these guys using algebraic combinatorics and the theory of symmetric functions. So let's start. So here is, of course, the dimer, the corresponding dimer. The lozenges themselves are just the connection of 2 triangles. They form a dimer. I haven't drawn the hexagonal grid underneath, but that's what it is. So actually, before we move on to symmetric functions, I can show you something that we can do without actually any technicalities. Of course, it's not obvious at all. But a lot of times in combinatorics, we use bijections which reveal a lot of what's going on. Of course, it's not easy to come up with these bijections. One of them is the Hillman-Grassel bijection. So instead of taking plane partitions, we'll take reverse plane partition. So now the numbers are increasing along rows down columns, but they are bounded by this shape. And I'm going to perform the following procedure. We're going to start from the bottom and try to move up if the numbers are equal, the one on top of the other is equal, otherwise we move to the left until we reach the boundary. So here, 2 is not equal to 1, so we have to move to the right, we stop. And we write 1 in the corresponding box, subtract it from here. Now we have the following, it's still a reverse plane partition, we continue. So now this time we can go up here, then go up here, and then we move to the right. And we record in this blue box exactly where the box which corresponds to where we started and where we ended. So this is the starting point is going to be the x coordinate. The ending point here is going to give you the y coordinate. We have a box in this square. We're going to put the number 1 here, and then we're going to subtract 1 from all of the numbers appearing here. We can continue this way until we reach all zeros. What do we get here? It's going to be some kind of an array. Okay, what's interesting about this array? If we sum up all the numbers in our reverse plane partition, is equal to the weighted sum of the entries in this array by what's called the hook ij. So basically how many boxes are below and to the right of whatever entry we have. So we have entry 1 here, the hook is 5. We have 1, 2, 3, 4 boxes plus the box of the entry itself. So it's 5, and then the other sum. This is the weight A. So to prove that, so Hillman-Grassel proved that this is actually a bijection from these objects to arrays without any restriction. Once you don't have a restriction, what do we have? It's a very easy way to actually sum things. So reverse plane partitions are equal to the sum of these arrays if we believe that this is a bijection. And because the entries now are independent, we can get this as a product over all these different entries. What's the weight? Well, whatever is written here, Aij. So we have a formula like this. So that's one way we can use actually to prove McMahon's formula earlier. So our plane partitions that are in a rectangular grid corresponds to reverse plane partitions in a rectangular Young tableau. Let's say it's an A by B. And then we just plug in this formula and we get this. And if you want to get the full McMahon, you can let A and B go to infinity, and you will actually get the original sum. OK, so now how do we generalize all this? We put more variables. More variables, x1, x2, and so on. And then we're going to have some formal power series in general, but we want to restrict ourselves to formal power series which are symmetric. Basically, they are invariant under any permutation of the variables. And if we have a finite number of non-zero variables, this would just be polynomials. So this is the ring of our symmetric functions. How do we understand this? We understand it using basis. So we have one thing is monomial basis, which the simplest thing you can think of. So m lambda x1, x2. So lambda is a partition again. So in everything I say, lambda is going to be a partition. So we're summing over all distinct permutations of the parts. We take whatever, x1 to the lambda 1, x2 to the lambda 2, and so on, and all the other permutations. So all possible distinct monomials we can get with that, with lambda appearing as the powers. So here are some examples, m11. This means we have one variable to the power of 1 times a different variable to the power of 1, and so on and so forth. M2 is going to be this. Here is another more complicated. So I'm restricting the number of variables so I can write a finite sum here. We can do that. So and 2, 1, 1, we have monomial x1 to the power of 2, x2 to the 1, x3 to the 1, and then all possible distinct permutations. And one can compute it sort of recursively out of restricting the variables as well. So that's one way to manage this, because it's a big sum. So do we agree that this is a basis for this ring? So basically, if we have some monomial, we know that all permutations will have to appear of this monomial. So if we have x1 to the lambda 1, x2 to the lambda 2, and so on with some coefficient, then all these other guys are going to show up there. So this is actually inside. So and vice versa. Obviously, this is symmetric by the definition. So as a polynomial ring, or as a vector space, actually, we can say that the dimension of the nth degree homogeneous component is exactly the number of partitions. So this is indexed by this lambda. So what other bases are there? Now we can do the power sums. So they are defined multiplicatively. So if we have just a single number here, single integer, then it's all powers of the variables to this. So x1 to the n, x2 to the n, and so on. And then p lambda is just going to be the product of all these p lambda 1, p lambda 2, and so on. So here are some examples. And as you can see, if we take, for example, p to 1, this is what it looks like. We can multiply, open up the brackets, multiply, and we're going to get a positive sum of monomials. I'll show you in a moment why we get those. So we can use a different basis, define a different basis. So the reason we are doing all this is because depending on what kind of computation you want, different bases can be convenient. So the homogeneous power sums, so we take all, now this time these are compositions, weak compositions as in the beginning of the example, x1 to the a1, x2 to the a2, and so on. So this is, in other words, all possible monomials we can get of total degree n. This is the hn. And then h lambda is just the product of all this lambda 1, lambda 2. And just to remind you what it was in the beginning, so if we evaluate it at 1, we get the same binomial coefficients we had earlier. Of course, the letters here change, so one can get confused by this, but it's the same. So we're just counting the number of weak compositions of little n into big N parts. We can do the elementary symmetric functions, which are going to be all square-free monomials of degree n, En, so there are no repetitions anymore. E lambda is just the product. This is also a basis. Nothing is obvious that these form a basis. What's the value of En at big N many ones? Well, you need to choose which variables you are using here. Big N, choose N, little n. And so why are these things bases? Well, because the transition matrices between each of these are invertible. That's the simple explanation. Why are they invertible? Well, depends. So depends on the way. So for example, if we expand p lambda in terms of m mu, this coefficient here, and you can play around and you will see how this works, is basically the number of ways to take integers lambda 1, lambda 2, and so on, and group them together so that the sum of these integers in each group sums up to the corresponding power of mu. So these are what we call set partitions. So with those constraints. And that's all, just you open up the brackets and you'll see how these things add up. What about E lambda and H lambda? So the E lambdas can be written in terms of expanded in terms of the monomials with this coefficient, and 0 is just the number of 0, 1 contingency tables. So 0, 1 meaning the entries inside are 0 or 1, such that the marginals in one direction sum up to lambda, and in the other direction sum up to mu. And the other coefficient is much bigger. This is like just non-negative integer entries with the same type of constraint, so many more. So if you play around with this, you'll see that this here, this p lambda mu, if you index it by, if you order your partitions in, let's say, lexicographic order, you'll see that this is a per-triangular matrix with non-zero entries on the diagonal. So it is invertible. So the p lambdas form a basis. With the e lambdas, it's a little bit trickier, but you can also convert it to an upper triangular matrix with ones on the diagonal. With the h's, doesn't work. So that's a different story, but the h's also, this is also an invertible matrix. And what kind of other relations do we have? So we have this Cauchy type identities. If we sum over lambda, we multiply the m's in one set of variables times the h's in another set of variables is equal to this nice product, 1 over 1 minus xi yj. So also if we do this product for the power sums, but we need to modify by this z lambda. And if we do this, the m lambdas times the e lambdas, we have similar thing, except now we have the dual version of this product, literally. It's 1 plus xi yj. And I'm saying, so one of the reasons that these things do show up in various statistical mechanics models, so this is a good thing to know. Maybe you'll recognize this in your own computations. And so on the next, any questions so far? So I defined a bunch of bases. Until you work with them, you're not really gonna have a feel for this or understand why we need it. But now I'll define the main culprits, so things that actually show up a lot in statistical mechanics. So these are the sure functions. And originally, they come from representation theory of the general linear group. So this would be basically maps, homomorphisms from n by n matrices to other matrices, so that the entries are polynomials in the entries of the original matrix, and they're satisfy the multiplication rules for the matrices here as matrices in the other set. And that's already quite complicated, but the way we study them is we understand what their reducibles are. These are the Weil modules, and they're indexed by all, it's called highest weights here, but in reality, because I'm denoting it by lambda, so it's integer partition again. One way to study representation theory is to study the set of characters. And these are just the traces. For any group, the character of the representation is just taking the corresponding group element. It's going to get mapped to some matrix, take the trace. And if you know the set of all this, you actually know the representation in theory. So it encodes all the information. And if you take the irreducible representations, the ones which we cannot diagonalize further into smaller blocks, their characters are the so-called sure functions. Okay, so that doesn't help that much in this case. So it's some very abstractly defined quantity. But it turns out we can actually compute them. For example, with this Weil character formula, the Schur function is a ratio of two determinants. It's xi to the lambda j plus, so depending on how many variables you plug in here, big N minus j. And the bottom I already wrote out as a product of linear factors xi minus xj, but it is actually a determinant. Which determinant? Vandermonde, yeah. So it is the same thing as above if you take the lambda to be 0. That is, it turns out that it factors. And why? How can you prove that? If you plug in the same variable twice in here, what's going to happen? It's going to have the same, this matrix will have equal columns. So it's going to be 0, which means that this polynomial up here is divisible by xi minus xj for all I different from j. So this is actually a polynomial in particular. And if you do the Vandermonde, that's going to be everything there is. So all you need to do is, because of the degree, that's all that's going to happen. Okay, so this is one way to define the Schur function. Punchline, this Schur functions form a basis for the ring of symmetric functions as well. So this is symmetric, this is q-symmetric, this is q-symmetric, so the ratio is symmetric. What other properties do they have? So here is an exercise. So if you want to compute some of those particular Schur functions, so let's say that we plug in partition, which is what we call the staircase, k minus 1, k minus 2, and so on up to 1, and you evaluated k variables, you're going to have this expression divided by this product. If you include the 2 power of 2 in the variable here, we have the same Vandermonde. So you're going to have the product of xi squared minus xj squared, which will cancel out with the bottom, and you get this. But in general, we don't have such nice formulas, so this is just an exception. What others? So we can compute the Schur function as a single determinant. Let's say that we have k non-zero parts in our partition, lambda 1 up to lambda k. Jacobi-Trudi identity gives us this, so the general term, let me, h lambda I minus I plus j. This is how it looks like. So we have a single determinant, and determinants are relatively easy to compute, but what's the problem with the determinant from a combinatorial point of view? So, okay, there's going to be a polynomial. Is it going to be positive, negative? Can you tell from the determinant? I don't know. Like, you cannot really. I mean, but it happens that these Schur functions are always a positive sum of monomials with integer coefficients. Well, integer coefficients we could guess from here, but that they're positive, not negative, is not obvious. What is the interpretation? If we take our partition, we take the Young diagram here. So in this case, I mean, things blow up pretty quickly, so I can only do that big of an example. So if we have the 2-2 shape, so the Young diagram, what we do is we put the numbers from 1 up to 3 in this case, depending on how many variables we have here, so that they're weakly increasing along rows and strictly increasing down columns. This thing here is called a semi-standard Young tableau. And here are all the ways I can form a semi-standard Young tableau with the entries 1, 2, and 3. And for each one of them, we record the corresponding monomial. So we have this combinatorial formula for the Schur function. So in particular, we know that these are polynomials with non-negative integer coefficients. And a bunch of other formulas. Okay, any questions so far? So now I'll tell you a little bit of properties that are maybe useful, other bijections that show up in statistical mechanics and elsewhere. But before that, we're going to use this that I just said to prove this McMahon identity again. So what was the... Let me just remind you of what was McMahon. This was like the partition, the fake type of partition function. What is pi? It's just a plane partition, so 5, 3, whatever. So integers decreasing. It's just an array of integers weakly decreasing in both directions. So let's take a rectangular Young diagram, A by B. So the notation here, it means that the parts are A repeated B many times. So the Young diagram will be a B by A rectangle. In this case, B is 3 and A is 5. So this is a semi-standard Young tableau by the definition I said earlier. I'm going to say that the entries are going to be between these numbers from 0 up to B plus C minus 1. So the entries are weakly increasing, strictly increasing along columns. So what happens if I subtract 0, 1, 2, and so on from the corresponding numbers on each row? So we're subtracting this as a vector. Then we're going to get weakly decreasing entries. And they're weakly increasing in that direction and that direction. So this is like a reverse plane partitions with entries from 0 up to C. So what's the largest entry that can be here is B plus C minus 1. But if we subtract B minus 1, then they're going to be between 0 and C. And what is this? This is just the rotated version of that picture here, except that now we are bounding it to take a particular shape. Okay, so these plane partitions or reverse plane partitions, if we sum up all the entries, this is going to be equal to Q to the minus whatever we subtracted here, how many times. And then what is this? The generating function for this thing. We're going to sum over all possible semi-standard Young tableau with these entries, which is we are going to do a Schur function, right? So S A to the B is the shape, and what are the entries? Well, whatever corresponds to here. And then we're going to take powers of Q, because when we want to sum up the values of the entries, we need to actually multiply Q to the power. We need to have exponential dependence in the variables. So 1Q squared up to Q to the B plus C minus 1. And now we can write.
Sorry, what is this? What does the 0, 1, 2 column mean?
So we're subtracting this vector out of everywhere here. I couldn't really write it in any other way. But I should have written we subtract the whole tableau of 0, 0, 0, 1, 1, 1, 2, 2, 2 from the entries. Yeah. So we are making the entries weakly decreasing this way, and we subtract first. Okay, so let's plug in the formula. I'm going to plug in the Weil determinantal formula that I showed you in the beginning. So it's the ratio of these two things. One is q to the b plus c minus I. These are these entries. This is our xi to the power of whatever lambda j plus b plus c minus j. And then we realize that if we take q to these entries, then the powers are exactly 0, 1, 2, and so on up to b plus c minus 1. So we have a van der Monde determinant, and we can factor it in this form. And now we can do some cancellations and manipulations. And if you don't trust the algebra, you can do it yourself. But in the end, if you simplify, so divide by enough powers of q, you're gonna get this expression: j from 1 up to b, k from 1 up to c, 1 minus q to the a plus j plus k minus 1. And here, just 1 minus q to the j plus k minus 1. And this is, so you may not recognize it immediately, but in Leo Petrov's talk yesterday, there was the same formula, except it was written, and that's, yeah, so it was written as triple product like this. And then we have 1 minus q to the I plus j plus k minus 1 divided by 1 minus q to the I plus j plus k minus 2. So exercise wired is the same. But they are. And of course, if you want to recover this original formula, then you just say a, b, and c go to infinity. And basically, that would make this term disappear. And then you'll have only the products at the bottom, which will turn out to be this thing. OK. Any questions so far? So, I don't know. OK, I have some time. OK, so let's move on a little bit of other properties that show up in statistical mechanics, and of course combinatorics. So I told you what a semi-standard Young tableau is. So what is a standard Young tableau? If we remove the semi, so that it's not a truck anymore. So, only. OK, so we have a standard Young tableau here. We take our Young diagram, we have some entries, and what we do is basically a bijection between these cells, and the 1 up to n is the total number of boxes, with the restriction that as you go to the right, the entries increase, and as you go down, the entries also increase. And all the different numbers from 1 up to n show up exactly once in this picture. So what does this look like? Well, if we take lambda to be, for example, this staircase shape, that's what we call a staircase, inverted staircase, you cannot walk on the bottom of it. So you can put the numbers from 1 up to 6 so that each number appears exactly once, and they increase down rows and columns. And how many are you going to get? Well, quite a few, in this case 16. I only wrote 8 of them, so these are the standard Young tableau, plus all the ones that you take by transposing the picture. It's still going to be a standard Young tableau. And how many are there? It's probably one of the few exact counting formulas we have in this subject. We have the Hooke length formula, which usually goes in the literature as the celebrated Hooke length formula. So you should realize this is a very special thing. So it's, well, it gives you from representation theory, which I didn't really tell you that much, but the dimension of the irreducible symmetric group representation Specht module index by lambda is also counted by these guys, the number of standard Young tableau of shape lambda, which we denote by this f lambda. So remember that f lambda is important, is equal to n factorial, the number of boxes, divided by the product of the hooks that I already mentioned. But here it is again. What's the hook? We take our box and we count how many boxes are to the right of it, down of it, plus the box itself. And we can write it in terms of the partition in this way. Lambda prime is just the partition which we obtain by flipping along the diagonal, the Young diagram, so the conjugate of lambda. So anyway, these are the hooks, and this is our formula, and we get 16 miraculously. Okay, so we can count this. Proving this formula is not easy by any means. Even if you can guess it, it's not so easy to do. You can prove it by induction. So if you have a larger shape, you can put the where can the number n go, and it only goes into a corner box. If you remove it, then you have a standard Young tableau of a smaller shape. So you can try to do that. It's not gonna be so easy to get the numbers to work out and group the terms and cancel things. But what we could actually do is you could prove this formula using Schur functions. Okay, so here is our Schur function again. So this is the semi-standard Young tableau that I just mentioned. We have this identity. So this time we have a weak inequality. So I already told you this, but there is a formula. The number of semi-standard Young tableau of shape lambda with entries from 1 up to big N is this thing here. How would you prove something like this? So the number of semi-standard Young tableau of shape lambda and entries from 1 up to big N is just the value of the Schur function evaluated at variables 1, 1, 1, 1, n many times. The rest is 0. Or, okay, so if you remember the formulas I showed you for the function, for the Schur function, if you plug in just variables 1 in the ratio, it's gonna be highly singular. So you avoid this by plugging in powers of q and then letting q go to 1. So we can do this. It's a polynomial. That's not a problem. And now we can use the Val determinantal formula as lambda. These are our variables. We can plug them in here. And again, switch the powers. So we have now these become variables. These are the powers. What is this? The van der Monde determinant again. So it's going to be a ratio of these things. And it takes some care to get to this form, but we can get out the q's, cancel things out. When you let q goes to 1, you can, if you want to apply L'Hopital, you just take the 1 minus q factor from each of them, and they're going to cancel on top and the bottom, and then you can take the limit q equals to 1 and get just the integers, the powers that are here. That's what will remain at the, as a number when you let q equal to 1, and you will get this formula. And in particular, so if we know that we have the number of semi-standard Young tableau is this, how do you get the number of standard Young tableau of this? So let me write a simple one. Let's say we have this thing. this tableau. I'm going to call the entries here x, y, and z. What is a SSYT? X less than or equal to y, x less than z. So we are going to have entries between 1 and n, for example, something like that. So what is, can we draw, how is the set of all possible x, y, and z look like? So these are integers, integer points in 3D in, I don't know if I'm gonna be able to draw this, but let's say x, y, z, x is less than or equal to strictly less than z, so it's, so this is the, so it's gonna be above this plane, and x is gonna be greater than, less than or equal to y, so there is going to be the other plane, and here, and if we cut it off somewhere on top, we're gonna get something that looks like this. More or less. So we have some strict inequalities here, so we're not going to take some plane or not. But, so this is just the scale, the dilution of a little thing here, a little polytope that stands over here. Let's say that this is 1. So we are counting integer points in this dilution. It's given to us by this formula. What's the volume of this little guy then? What's the volume of the big thing? So if you know how many integer points it has, the volume is kind of around the number of integer points, plus minus smaller order terms. But you're scaling over n. So we can scale back over 1 over n, so we can think of a refinement of this little polytope here by cubes, by little cubes of size 1 over big N. And then as we let n go to infinity, the number of integer points is going to approximate the total volume here. So what's going to be the number of, so if we scale it back, what is the number of discretized things is going to be 1 over n to the lambda times whatever this product formula is, hij. So this is going to be product of 1 plus this thing divided by hij. When n goes to infinity, where does this go? Goes to the product of the hooks. Okay, so but another way we can think of this polytope is if we look at all possible arrangements of the variables. So we can have either this. Okay, we ignore the boundary for a moment, or we can have this in this case. Each of these gives us a simplex. What's the volume of a simplex? 1 over 6 in this case, 1 over n factorial. So in general, it's like 1 over n factorial, 1 over n factorial. And how many ways can we divide our polytope by such simplices? As many as we can actually order all the variables in absolute order. And what is this order? This is exactly standard Young tableau. So the number of standard Young tableau times 1 over n factorial is the volume of this thing, which happens to be this. So we have hook length formula. And this is what this is saying. So of course, this is not the simplest proof because you need to develop a bit of the theory of sure functions in order to do that. But if you already have this, is one way to get it. Okay, any questions? All right.
That's like the dimension of the representation?
Yeah, that's the dimension of the representation, of the symmetric group representation. This is the dimension of the general linear group representation. This is for the symmetric group. So I didn't explain the duality and all this, but there is.
Is this something you can generalize to count linear extensions of arbitrary process?
Absolutely. That always. So this is nothing special about standard Young tableau. If you want to know linear extensions of partially ordered sets, then you can count integer points in the order polynomial, then you get the linear extensions are the leading term of the order polynomial, actually, divided by n factorial. So this holds in general. Of course, the problem is we never have formulas for either. So we actually happen to have a formula here. And okay, so in general, but if we restrict, so there is this thing called the Koska number, so number of semi-standard Young tableau of type mu, meaning how many ones, twos, and so on show up. It's what's called the Koska number. And this is actually the, when we want the same coefficient when we want to expand the Schur function in terms of monomials. And by a certain duality, which is I'm not going to mention here, that if you want to expand the homogeneous in terms of Schur functions, what can we say about each of these individual pieces? So we have the nice big formula. What about them individually? And the problem is, so if we want to decide, is this zero? This polynomial, actually, this is just dominance order. All you need to solve is a bunch of linear inequalities between lambda and mu. So you can figure out whether the Koska coefficient is zero or not very quickly. But if you want to compute the value, first of all, we don't know of any nice formulas. And in fact, it's what's called Sharpe complete, meaning there isn't going to be a very nice, efficient formula when lambda and mu are in binary, thanks to our program member Hari Narayanan. But we also conjecture that even if you shrink your partitions in some sense, then it's still going to be what's called Sharpe complete. So anyway, so there is some computational complexity that we use here to describe just how bad things are, and things do get pretty bad very quickly when we don't have exact formulas. So what else do we have? We have this thing called RSK. So the laser pointer. So we have two identities. So this basically comes from representation theory directly if we know how to identify the standard Young tableau. If we sum over all lambda, f lambda 2 squared is going to be equal to n factorial. There is also this other identity. So remember this factor? This thing showed up earlier, so it shows up again here. So summing over all lambda, the Schur functions are like orthonormal basis to a certain inner product, and that's basically what it means. So how do we prove something like this? So there is this Robinson-Shenstein-Knut correspondence, also very celebrated, appearing everywhere. So we take a matrix, m by n, let's say in this case matrix with non-negative integer entries, and we assign to it a pair of semi-standard Young tableau of the same shape. What is the shape? It's a different question, but it's going to be the same shape. And the type, meaning how many numbers of each kind, are given by the marginals of this matrix. So here is an example. if you believe me that this is correct, so I performed this algorithm I'll show you in a moment. We got the two same shape semi-standard Young tableau. So how does the algorithm work? We take our array, we form the generalized permutation, so we read the array, let's say, row by row. For row 1, we write the column index as many times as the entry is here. So here we have 1, 3, because this is the first non-zero entry. We have 1, 5, this is the next non-zero entry. Here we have 2, 2 in the next column. Now we have here an entry equal to 2, which means that we repeat 2, 4 twice. Then we have row 3, and so on and so forth. And how does the algorithm work? We're going to start inserting things, reading this double array one by one. First, we start with two empty tableaus. We insert 3, 1. 3 is going to go in the blue thing. 1 is going to go in the green thing. How? Well, in this case, there isn't much. We just put 3 as in a box to the first place we can. And then we put 1 in the same box on the other side. Now we're going to put 5, 1. We're going to try to put 5 here next to the 3 if we can, if we could steal a semi-standard Young tableau, and then we're going to record 1. Yes, we can. We can put it right after, and then we record 1, 1. Now we want to put the blue 2 here. But if we put it afterwards, it's going to mess up the order. So what do? We find the first entry that's bigger than 2, and we bump it out, and then we continue the process with whatever was bumped out here, in this case 3, gonna go to the next row. So we're gonna insert it in the next row without a problem in this case. So we have this tableau, and then we are recording the other entry, the green entry, exactly where we added the box. So every time we're gonna add a box in this. And we keep going. So 4 is gonna bump out the 5 is gonna go to the next row, and so on and so forth. If you continue, by definition, they're going to be the same shape. This is going to be semi-standard just by what I told you. I mean, it's not so obvious that it's strictly increasing down rows, but it is. Q is also going to be semi-standard. It's more obvious maybe, but they're two semi-standard tableaux, and this procedure can be reversed. And so we have a bijection between these two entries, and we get this identity, the RSK bijection. So there is another way to see the RSK bijection, which is more statistical mechanical in some sense. It's what's called vertex operators. So if we have a box, so we're going to apply this on the matrix. We have an entry A, and we have 3, on the 3 corners, we have Young diagrams. So they are going to satisfy some condition. Mu is going to be just 1 box larger than lambda, and nu is going to be 1 box larger than lambda. We define the shape, the Young diagram row, following some procedure, which basically is an algorithm of how to compute it step by step. Piecewise linear function, as you can see. So how does this look in practice? So this time we're going to grow from the bottom to the top. My array A is slightly reversed in this case. We put empty Young diagrams on the borders here and here. These are these parameters, and we start building this up wherever we can. Whenever we have 3 Young diagrams, we can fill this up. And this is well defined. You can think about this for a moment, but we cannot really build somewhere else on top before building up from the corner. So the interface here is always going to be some actual like lattice path or Young diagram. So here if we follow this procedure, whatever it says, we're going to get a box. Here we're going to put 2. We have some differences. We're going to get 2 other Young diagrams. And so on and so forth. So we got this. So these are our partitions. They're drawn just to visualize this. And now where are the semi-standard Young tableaux? The semi-standard Young tableaux are made by stacking up the things that are here on top of each other, and the entries in different colors that remain are going to be 1, 2, and 3. And the other tableau is going to be this one. So we read the top row of this guy. These are our partitions. We stack them up on top and enter the numbers in whatever colors remain. Like this. It's a semi-standard Young tableau somehow. It needs to be proven. And the recording tableau is the other end. And we have it. So what's the good thing about this procedure? Symmetric. Like in the previous one, I was inserting one, recording in the other. But here, whatever's happening on this side, it's like the same type. The algorithm doesn't distinguish between mu and nu, between this end and this end. So if I flip the whole thing, I'm gonna flip the end result as well. And of course, and so these are the same P and Q that we'll get if you perform the RSK the way that I described earlier. So one thing we see is that if we transpose our matrix or the original array A, we get transpose of, we switch the Young diagrams. So that's another way to do this, and these are like local operators, so you get different information from this point of view. So you can also use these vertex operators to, so of course RSK is proving this identity by, if you believe that this is a bijection, then if you apply the bijection, you get exactly the Schur functions. And these growth diagrams allow us to actually prove a more general identity, so we can do skew Schur functions and have this. I didn't define skew Schur functions, but basically that's the way you define them. You take 2 shapes, one inside the other, and you take everything in between the 2. This is a skew Young diagram, and then we define a semi-standard Young tableau the same way. We fill in the entries weakly increasing along rows and strictly down columns. So this is a skew semi-standard Young tableau, and we sum over all of this. So this is still symmetric and possesses all sorts of nice properties, which maybe I'll mention tomorrow. Depends on how much time we have. And so one very important property of RSK, which shows up if you study last passage percolations and polymers and all that. So let me show you on the level of combinatorics. So let's take some kind of word, basically a sequence of integers. In an increasing subsequence is any subsequence doesn't have to be consecutive entries, which the values are weakly increasing along the same reading order that we are actually reading our word. And the longest increasing subsequence, which I'm going to denote here by IS1, increasing subsequence 1, is the maximal k for which you can find k increasing entries in this order in the word. So if we take W to be this permutation in this case, the longest increasing subsequence would be given, for example, by 3, 4, 8, 9. And if you inspect this carefully enough, you'll realize that this is as long as it can get. So the longest increasing subsequence is 4 in this case. And we can define the more general collection of j different longest increasing subsequences that are disjoint, and altogether the total sum of this is maximal. So here is a theorem of Curtis-Green, which is generalizing a theorem of Schoenstatt, is that if you perform RSK on our word, we get two same-shaped tableaux of shape lambda, then the first j rows are giving you the sum of them, the number of the size of the first j rows is giving you exactly the longest increasing subsequence, the j longest increasing collection of j increasing subsequences. And in particular, the longest increasing subsequence of a permutation is equal to lambda 1, the first entry in the partition shape, which we're going to use tomorrow to derive the statistics for longest increasing subsequences, an application of all this. So here is an example, very short example, but it gets complicated. But so 2, 3, 4, 5 is the longest increasing subsequence in this permutation. Its length is 4. It's exactly as long as the first row. And here we can split this permutation into two increasing subsequences. Notice that neither of them is longest, but altogether the length is 6. Whereas if we took the longest subsequence here and we just tried to find another increasing subsequence, we will get just one more. So that definition is already tricky. It's not that simple. So we have these identities. And one way we can see this on our pictures, so if we have the final shape here, lambda 1 is going to be the path with the largest weight when we sum up the entries along in an increasing direction to the left and up. So this is like a longest increasing subsequence in our generalized array. And this is also going to give us lambda 1, which one can actually prove using these growth diagrams. And then lambda 1 plus lambda 2, actually the two longest ones can be given by this. And so on and so forth. Okay, so I have 5 minutes or something. Okay. So let me see. So here is what you saw this morning. Okay, so lozenge tilings. So I'll just show you very short applications. So these are our lozenge tilings. We can think of them as dimer models of the hexagonal grid, and so on and so forth. This was already explained. And here is the complete, in this case, when we have the dimer model, here is our picture. Here is a big one, thanks to Leo Petrova's simulation. So the question is, of course, how do you study properties of these pictures, especially in the limit? So one thing that was already mentioned by Cedric is that we can think of this as non-intersecting lattice paths. So how we draw the lattice path, matter of convention. So one way, I think what Cedric was saying, we can follow the black dots here. We're going to have a collection of 4 non-intersecting lattice paths, or we can follow the red dots in this picture, which is going to give us another collection of lattice paths, which is also the 5-vertex model, which you hopefully will be explaining later in the tutorial. So long story short, these things here can be studied often as collections of non-intersecting lattice paths. So these are 3 lattice paths, they don't touch or intersect each other.
Greta?
Yeah?
I didn't get. How do you get the red? What do you do with the red points?
So here, so I guess, okay, here I didn't draw the remaining red. So here we have black on top going all the way and red on bottom. And I'm gonna draw them row by row. So I will, so the way these are drawn, so I'm gonna make them horizontal and shift a little bit so that they line up on top of each other. And then basically, on every row here in this picture, I'm going to select that it's gonna show only 3 red dots. So you see 3 red dots. So the first row is this one that's not shown. The second one is this one that's this guy. So we have like red, red, black, black, red, black, black, right? And then so on and so forth. And now I'm going to follow. Imagine that the red dots are labeled in this order that they appear. Now we're going to connect the corresponding dots on each row. So they are like moving along this line. So tacit actually, in some sense. But anyway, so that's actually I don't want to get into this because when there are gonna be lectures about this more detail later. But anyway, so the point is there are non-intersecting lattice paths. Here is another one from Vadim's book. Another way to do non-intersecting lattice paths in like the dual picture in some sense. And we can also put them on a grid. We can stretch and shrink it, whatever, move things around. We can get to a picture that looks like this, maybe. So here, this is the general theorem. I mean, I've drawn it on the square grid, but you can actually play this game in all sorts of other grids, you know, acyclic graphs, planar graphs, whatever you want. It's always going to work. If you want to count the non-intersecting lattice paths that connect A1 to B1, A2 to B2, and A3 to B3, like in this picture, then this is actually a determinant. And what are the entries of the determinant? In each entry, you are just going to count the number of paths from AI to BJ. So forget about the rest. All you're doing is counting paths in this lattice or whatever graph you want. Well, planar it needs to be planar because you need to be able to intersect things when they cross over. So that's actually one requirement. So it is a determinant. Proving this, it's not so hard. If you expand this determinant, every time you crisscross endpoints, of course, we are going to topologically here, we're going to have an intersection. And you can define an involution of changing endpoints by switching how you label the lattice paths that intersect. And that's going to clear the way and cancel out everything you get here, except the ones that never intersect.
Can I add this? If you didn't try this for 2 paths. Okay.
Yeah, so you are going to apply this for 2 paths. And yeah, you should try this. Try this at home, it's safe. Okay. Anyway, so here is the proof. There is a sign reversing involution. It's really one of the most beautiful things we have in combinatorics. And let's go back to our Schur functions and semi-standard Yang tableau. Okay, so here we have a semi-standard Yang tableau. I've colored the rows in different colors. Each of them I'm going to plot on this grid. How do I plot it? Plot it as a lattice path. So I take the first row, 1, 2, 3, 5, 7, 7. Gonna start at 3 So I have 4 rows, so they're going to start at 0, 1, 2, and 3. I'm going to think of this as the top row is like the last thing here. I'm going to start at 0, and then I'm going to go to level 1 where I have these entries. And for each entry, I'm going to take a horizontal step at that level. So here we have 2 1s, so 2 horizontal steps at level 1. Then we go to the next level, 2 horizontal, 3 horizontal. Then there is nothing 4. So we just go straight up to 5, and we have this 7, whatever, and then we go off to wherever you want. And then we are going to do this for the next guys. Okay, so first thing, not so trivial to see that because this is a semi-standard Young tableau, these paths never intersect. So first of all, they're like upright lattice paths because of the weakly increasing rows, but because of the strict increase, we never have them touching. And where do they end? Well, depends on the length of the row and also where it started. So there is this shift going on. So these are the horizontal coordinates of their endpoints. And now if you believe the Lindstrom-Gesell-Vienot formula and what I just told you that these are non-intersecting lattice paths, we can count those, and we can count them with weights because the formula also takes into account if we assign weights to each of these paths. Maybe for the horizontal one steps, we have x1, x2, and so on, like this here. On the one hand, we have semi-standard Young tableau, which are our sure functions with these weights. On the other hand, how many paths of like this go from some point to some other point without any other restriction? This is exactly the number of all the different monomials you can write. So a bunch of x1s, a bunch of x2s, and so on, for all possible. These are going to be the homogeneous symmetric functions that I showed up in the beginning, just by definition. And now Lindstrom-Gesell-Vienot is basically telling us that this sure function is going to be the generating function with a weighted non-intersecting lattice paths from these points here are the starting points, these points here are the end points. It's going to be a determinant. For each entry, we have the paths from AI to Bj, which is exactly the homogeneous symmetric function, and we just proved the Jacobi-Trudy identity, which I showed earlier. And that's it.